Good afternoon, everybody. Good morning for those who listen to us from the US, or good evening from those who listen to us from Asia, and a very early good morning to Aditya. I just was informed that 3 a.m. in the morning, I know where he is, and we have to thank him very much, for getting up so early to give us this talk. This is the International Space Science Institute in Bern, Switzerland, with its Game Changer series, where in this series we look at habitability from galactic to microbial scales. And today we have a talk on life as an agent for sustaining habitability. Now, we've talked about habitability in previous talks, but Aditya is asking the question, is what kind of habitability for sustaining life or for getting life started, and how, does habitability change with time as the planet evolves, and could, life have an effect on the potential of a planet to keep on sustaining life? And we're looking very much forward to having him explain this to us. He is a visiting fellow at the Research School of Astronomy and Astrophysics at the Australian National University, and is using our current knowledge about the origin and evolution of life on Earth to look for the potential and the nature of life elsewhere in the universe. One of his themes is, how could a planet keep life, sustainable on its surface? His hope and idea is that his research would, eventually also lead to be able to define biosignatures with which we might detect life on other planets. Without further ado, Aditya, the floor is yours. Just let me say that this talk is recorded, so if you missed the talk, or if you want to revisit the talk, you can visit our website and replay it. And also, let me remind you of our newsletter that you can subscribe to from the bottom of any of our web pages. But now, Aditya, please, the floor is yours.
Thanks very much, Tillman, and thank you everyone for joining us today. I want to start with letting you know that it is 3 a.m. in the morning. So if I do miss things or start making mistakes through the talks, it will be recorded for eternity on YouTube. So that gives me a lot of pleasure. No, it doesn't. Feel free to put your comments in chats. I look forward to the feedback from you all. And hopefully we'll have enough time for questions at the end. But if we don't get to your questions, then more than happy to have a conversation later on as well. The aim of this session, I guess, is to hear as many ideas on the hypothesis we are presenting. So every idea, every comment is more than welcome. Over recent years, astronomers have been looking up and out with telescopes like Kepler, ground-based observatories, and more recently with telescopes such as TESS. We have found a lot of planets beyond the solar system. Now, here are some artists' impressions of what those planets might look like. Many of them might be even habitable. We don't yet have photographs of these locations, but very soon we will. At the same time, the biologists have been digging deep here on Earth. They've been getting their hands dirty. And I think it's fair to say that over the last 2, maybe 3 decades, what we have realized is that there are many different habitats for life on Earth. There are places where we didn't once imagine that life could exist. So in the polar ice caps, or deep in the hydrothermal vents where it's really hot and acidic, or really basic, or even next to nuclear contaminated sites. But everywhere we have looked on Earth, there is life, at least where there is some form of liquid water, even if it is just a molecule thick layer, we seem to find signs of life. what that has done is change a scenario which perhaps when I was doing my high school or undergraduate years, where it was about there were a range of terrestrial environments known to harbor life on Earth and a range of environments known to exist beyond Earth. And there were two different parts of this Venn diagram. But over the last 2 decades in particular, these have started to overlap. And that's what we mean by habitable planets. So Earth is definitely one of them, but there are many more. Today, for example, you can see visualizations like this, where the 5,000 odd planets which have been detected around other stars can be ranked into how habitable they are. Here, for example, is one around Proxima Centauri b, the star, and it's about the size of the Earth, and it's considered to be one of the most habitable planets. We could go through each one of these and talk about what we mean by habitability, but again, you know, in a few years, we should have the technological capability of being able to characterize the atmospheres of these planets, perhaps even detect signs of life on some of them. These are not just the planets that could have life on them. There are many more. This is an image from the Hubble Deep Field that shows about 15,000 galaxies in this frame. Each of those galaxies has billions of stars, and this frame is one tiny fraction of the entire night sky. So if you were to extrapolate the planets we've detected to the planets that could be out there, that's a big number. As people like Carl Sagan would have said, billions and billions of habitable planets out there. Now, life was not always present in the universe. At the moment of the Big Bang, we can be pretty sure there wasn't life in the universe, at least not life as we would define it or know it to be on Earth, right? It took some time for the first molecules to form, for the hydrogen gas clouds to collapse on themselves and ignite the first generation of stars. During the first 2 billion years of star formation, the abundance of rock-forming elements, things like iron, magnesium, and silicon, were probably not high enough to produce rocky planets that were big enough to host a volatile-rich environment of liquid water and hold an atmosphere that was conducive to life. So for between 13.8 and 11 billion years ago, we can be pretty sure that there wasn't life in the universe. But beyond that point, it's a different story. After passing through the elemental bottleneck about 11 billion years ago, we are safe to say that all the fundamental ingredients for life are present. What I mean by that is elements like carbon, oxygen, nitrogen, phosphorus, sulfur, the elements that are created by generations of stars and then can combine into molecules that produce the building blocks of life. Things like amino acids, the genetic material that is DNA or RNA, the molecules that allow energy to be transferred from one molecule to the other. All of these things require these set of elements, and we think they were present after the first 2 billion years of star formation. From about 11 billion to 5 billion years ago, wet, rocky, Earth-like planets were in the circumstellar habitable zone. We'll talk about these in a minute, but they started forming and evolving. It's therefore reasonable to speculate that life may have emerged many billions of years before the emergence of life on Earth. So the Earth is about 4.5 billion years old, and it could be the case that 6 billion years before that, there could be life elsewhere in the universe. So the Earth wasn't the first place where life evolved. There might have been other places where life had a head start. And it may have become complex as well. That raises the question, where is everybody? We've got all these potentially habitable planets in the universe, perhaps with a head start compared to when Earth had the emergence of life. And yet we haven't found aliens, whatever the word aliens means. This is also known as the Fermi Paradox, and I'm sure many of you are aware of that. Frank Drake is one person who has tried to use the concept of the Fermi Paradox and understand it using the Drake equation. Now, again, it's a concept that I think many of you would have come across previously, but the Drake equation tries to identify the number of civilizations in a galaxy with which communication is possible. That's the N. And it's a function of the rate of star formation per year in a galaxy, with the fraction of those stars with planets, FP, the average number of those planets that may develop an ecosystem, NE, and then the fraction of those planets that have life developing on them. And the list goes on, identifying the fraction that have intelligent life, and the ones that go on to have interstellar communication, and then survive for long enough to continue to send those communications so that we might one day detect them with telescopes that we build on Earth. This concept, I think, is quite useful to think about where we've moved in this search for life beyond Earth and the field of astrobiology in general, because I think over the last 3 decades in particular, astronomers have identified there's a lot of stars forming in our local neighborhood, and indeed there's a lot of those stars have planets around them. It turns out that if you were to look up at the night sky, many of the stars that you see with your naked eye probably have about 2 planets in the habitable zone of those stars. That's a number that's based on the statistics of Kepler telescope, looking at sun-like stars and thinking about Earth-like planets in the habitable zones of those stars. We are starting to get an idea, thanks to more recent missions, of the number of planets which are Earth-like. That is to say, they are Earth-size, they might have a liquid water around them, they might have the conditions for plate tectonics, and so on. But the rest of the terms are a bit more vague, is probably a good way to put it. So we've got a pretty good handle on these terms, and they look like they're pretty big numbers, but what happens to the rest of them is still a bit uncertain. They generally relate to concepts like the origin of life. If the origin of life is a really hard process and a really, a process that has so many steps involved that we have to get everything just right, then FL will be really small. But if the origin of life is a deterministic process that happens the moment you have the right conditions on a planet for the emergence of life, then FL would be really big. FI, the intelligence fraction, is again more to do with the biology and what we think is a likely outcome of biology. Now, if you think about Earth, humans are one intelligent species. Indeed, crows and whales and other things are also intelligent, depending on how you define them. So there seems to be some intelligent forms on Earth, but I think it's probably safe to say that intelligence doesn't seem to be something that evolution moved towards in general. So I'd like to suggest, for argument's sake today, that maybe FI is a really small number. How many of the civilizations on Earth or species on Earth have gone on to build radio telescopes or the Starship Enterprise? 1 out of the millions or billions of species, depending how you define it, over the history of our planet. The final term, L, is to do with how long that civilization lives. Now, as you can probably all guess, we are closer to an extinction event, at least for humans, with the threat of a nuclear war than we've ever been before. And this could take place elsewhere too. There are other threats that can curtail the lifetime of that civilization, be it an asteroid hit or any other disease or whatever it might be. And these are all factors that have been suggested previously as one possible explanation to why, despite having really big numbers here, n is approximately equal to 1. That is, we might be alone, and this is why we haven't found aliens or seen aliens or been visited by aliens as yet. You can find many more solutions than the ones I've described here if you read the book by Stephen Webb. There's a book in 2015 called Where is Everybody? 50 Solutions to the Fermi Paradox. It got upgraded to 75 solutions of the Fermi Paradox. Now, what we are going to talk about today is actually not one of these 75 solutions. So it's something different that you won't find in that book. And that's what inspired Charlie Lineweaver and I at the Manstrommel Observatory in Canberra. Some of you who have been to Canberra at ANU will recognize these observatories there. And Charlie and I started thinking, what contribution can we make to this field that hasn't been discussed already in those 75 solutions? And in 2016, we published a hypothesis article in astrobiology. And I'm hoping that today I can share with you some of the concepts we presented in that paper and some of the insights. And yeah, look forward to hearing your thoughts on it later on as well. So the paper is titled The Case for a Gaian Bottleneck, the Biology of Habitability. Now, there are many factors that influence planetary habitability. Here's a figure that illustrates from a review paper just some of those factors. They range from stellar effects, so things like the type of star it is, the age of the star, what kind of magnetic fields or wind, stellar winds come out of that star and what that means for life. There's a concept of the planetary system. So what does it, how do these planetary systems form? What does that mean for a planet that is Earth-sized in the habitable zone of that star in terms of its composition or volatile delivery, or the impact flux when life is emerging on a planet? Then there is the planet's property itself. So how big is the planet? What's the albedo of the planet? What's the atmosphere made up of? How does it evolve over time? Does it have its own magnetic field that can counter the effects, or often the negative effects of its host star? And so there are a whole range of different factors out there. The one we'll be focusing on today is biology. And it is in fact one of the least understood, I would argue, of these planetary habitability factors that are presented here. Now, it's worth mentioning that habitability is not the same as habitable zones. Often we confuse these two concepts. And indeed, recently in the series, the talk by David Catling on habitable zones is quite an interesting talk. So if you haven't seen it, I can highly recommend it to watch it online. But I just want to revisit some of these ideas so that we have clarity when we go into some of the details. So the circumstellar habitable zone is also commonly known as the Goldilocks zone. You might have seen figures like this whenever exoplanets of interest were discovered in the habitable zone, that, oh, we found a planet that is in the Goldilocks zone. It's not too cold, not too hot, it's just right. And what that means is it's far enough from the star that water on the surface is not going to boil over and escape, and it's not too cold that it's going to freeze over. As I mentioned, we think based on the statistics of the exoplanets that we've detected, there are about 2 planets in the habitable zones of most stars that you see up in the night sky. This is a figure from last year that tries to show all the planets that have been detected so far using a range of techniques. and where they lie in this Goldilocks zone. And so this box is what translates to the Goldilocks zone. So it's about the size of the Earth, but it's in this just right category over here. And we found a few planets, but most of the planets we have found are not in this region. And that is not because they don't exist, but because our techniques that have been used are generally more sensitive to planets that are bigger than the Earth or closer in to the star. And so we've populated this part of the graph really well. And we still have some blanks here, but increasingly we are starting to fill this blank. And I expect that in a decade or so, this will be quite populated. And you know, we'll have many Earth twins out there to understand and to study. Here's that habitable zone chart. That's the classical view or the classical figure that you often see, where there are different types of stars, and the hotter the star or bigger the star, the habitable zone tends to move outwards. So kind of makes sense. If it's a hotter star, you have to move further away from it so that it's not too hot, right? And the Earth happens to sit right in this green region. Now that's because we've arbitrarily defined that as the nice region because we are there. Here is a different view of that same figure. And you can see Earth over here, right in the middle, with a few of these example exoplanets that showed up as potentially habitable. Note again, Venus is outside because it's too close to the star, and Mars is just outside. Now, this is not a static view of habitable zones. There is temporal dependence, right? So over the age of the star, the shape of that habitable zone does change. Here is again on the same axis of stellar mass and distance. This is what the habitable zone would look like when the sun started. So this is a zero-age main sequence star. You can see that Earth is habitable, Mars and Venus are just on the boundaries. But at the end of the main sequence of our sun, the shape of this curve will change such that Earth is outside it. It will get too hot for the Earth to continue to sustain a liquid water surface. And Mars, in fact, could become more habitable. So it's important to appreciate that habitability is not a static concept. It changes with time, not only because of the evolution of the star, but the planet itself. Here is an example from a paper by Charles Coquelle where they talk about Mars. And over here, what we are looking at is a schematic diagram of how the habitability of the surface of Mars and the subsurface of Mars would have changed. So here, if we start at the formation of Mars, Mars could have been completely uninhabited or inhabited. In this model, which is a kind of simple one, it's a red planet. There's no liquid water, never was habitable, and life never emerged on it either. Or there was liquid water, which is what we think is kind of true based on isotopic studies of Mars and looking at the geological features that are present on Mars today. There was an ancient water reservoir covering about 20% of the surface. And since then, Mars has lost some of that water, a lot of that water, it turns out. But it was never colonized by life, right? There's no green stuff like you see on this half of the diagram. And even if there was life on early Mars, maybe it was isolated to certain portions of that habitable region on the surface or the subsurface. And today, it continues to be present only in isolated pockets. So as we send missions or explore Mars further, maybe we'll find these little pockets and find signs of active life there today as well. So habitable planets evolve too. Another concept in habitability is how the conditions required for the production of the building blocks of life are actually quite large and big. And there's no scale associated with this diagram. It's a conceptual diagram, but the conditions required for abiogenesis, that is to say, for the emergence of life, for the origin of life, are much smaller, much more restrictive. Once you have the emergence of life, then perhaps life can learn to occupy more of the n-dimensional or multi-parameter space. This is, again, a nuanced concept, because we often think, oh, life got started so on a planet, and so because it's the habitable zone, but we forget to think about how that habitability changes and what the requirements for habitability change. So maybe the conditions for the emergence of life are actually not compatible with the conditions for sustaining life, right? And there's so many different factors in here that it can become a complex and vague concept. And this is why Charles Coquelle in a review paper on habitability used the line, habitability is a commonly used word. Its usage is usually vague. We have a pretty good idea of what we mean by habitable when we talk about it with each other. You know, we talk about, oh, there should be an energy source, there should be elements that can build the blocks, there should be some sort of solvent, most likely water, and the right physiochemical conditions. But the moment we start drilling more than this idea, it kind of becomes hard to know what we're talking about. So it is a fuzzy concept, and I suspect it will remain that because it's quite a complex field. Part of the reason for that is, even though many of these habitability parameters are starting to be modeled and simulated, they generally tend to be physics and chemistry dominated. So astronomers or earth scientists or planetary scientists putting, you know, their really complex code, often maybe written in Fortran versus newer programs, putting these ideas together. Now, biology is exceptionally hard to write in equations that you can analyze using a computerized script. And so the tendency is that most of our conversations in this field have been around the physics and chemistry-based concepts. So the biology of habitability gets lost, even though I think we all recognize that there is a role for biology in that concept. So here is one figure that we will kind of use as our starting point to talk about the biology of habitability. And we've talked about the conditions required for the origin of life. Another way to say that is the Abiogenesis Habitable Zone. Imagine that 4 billion years ago, you can think of the Earth right now. The A and Z is all the conditions that you need for the origin of life. So for argument's sake, let's say you need to have water, you need to have the right pH, you need to have the right salt concentration, you need to have the right chemical redox states, and the list could go on. Now on Earth, there were only some parts of the Earth that overlapped with that A and Z. And over there, life emerged 4 billion years ago. But then Earth evolved, like we've talked, planets evolved, sometimes because of the factors from the star, but more generally, the geology on the planet, just through geological cycles, will tend to cause the planet to evolve as well. That could be in the atmosphere, that could be on the surface. And so it is plausible that the A and Z is no longer present on Earth. That is to say, there are no places on Earth where life is emerging today, because the conditions that were needed for that are not compatible with the conditions for the sustaining of life on Earth today, right? So today, they're quite different from each other. And in the future, that the same thing will happen. And what we have is a range of inhabited environments and places on Earth where there's still no life. So in the core of our planet, there is no life. There is only life as far as we know where there's liquid water present. This brings us to this figure, again, a conceptual one, as we build up our understanding about the biology of habitability. Here we have habitable conditions and the A and Z, so the conditions required for the emergence of life. And here are the planetary environments, the same blue region that we saw here. Now, if the planet wasn't evolving, this is what we would see. But like we showed in the earlier figure, we know that planets evolve over time. Now, if there was an emergence bottleneck, this is the scenario that would take place. That is to say, there was never a time in Earth's history or a planet's history when the abiogenesis habitable zone overlapped with the planetary environment, right? So there was never an emergence of life. And within a few billion years, perhaps, any prospect of life emerging was extinguished because the planet evolved too much. It never had liquid water, for example, to support the emergence of life. An alternative view is that the emergence bottleneck doesn't take place. So that's when the origin of life seems like it's a deterministic process. You have the right conditions, the origin of life will take place. And as a case study, I want to use these three planets. Here's Venus, Earth, and Mars, as we would see them today. But 4 billion years ago, they might have looked quite similar. And that's because they probably had very similar formation histories. They probably all had liquid water, from what we can tell. And they probably all hosted life forms. Even if life did not independently emerge on all three planets, it's safe to assume, given the impactor rate and the dynamics of the inner solar system, that there was planetary exchange going on. So if life did emerge in one place, it could have got transferred in a relatively short time scale to another place, particularly if it was a microbial life form. If we think about artists' impressions of what the early Earth looked like, I'd like to suggest that this could be early Venus or early Mars. And it is only today that those planets have diverged in their planetary evolution history because of a range of reasons. Perhaps biology was one part of it, as we will see in a few minutes. But I want you to imagine a scenario that there is no emergence bottleneck and life gets started on all three planets. What happens then? Well, you could have a scenario where the A and Z does overlap with the planetary environments. So life gets started, but it goes extinct. For argument's sake, let's think of Venus or Mars. Life got started, but went extinct within the first billion years. Venus went runaway heating, and Mars went runaway ice albedo or runaway glaciation, where its liquid water was lost to the subsurface or frozen in the ice caps and then gradually sublimed away into the atmosphere and into space. The Earth, on the other hand, was one where life got started, but it hung on, and it actually expanded the range of conditions and environments that were present on Earth, such that it still continues to be present today. It's almost like life has this capacity to change, perhaps not by intent, but through natural selection, through the normal processes of evolution as we see, to select for conditions on a planet such that it makes sure that it remains habitable for itself over the next few billion years. Eventually, all life on Earth will go extinct. We call this a late extinction. So about 1 billion years from now, the sun will have evolved to the point where the Earth will no longer be habitable, regardless of what life can do. And at that point, the Earth will evolve away from habitable conditions as well. And we term these two scenarios, one called the Gaian bottleneck, early extinction, and the other a Gaian regulation scenario where there's late extinction. We'll explore these in a bit more detail through a range of different figures as well. So why do we invoke Gaian regulation to explain the persistence of life on Earth? I said, think of Venus and Mars in this scenario and Earth in this scenario. Why do we need Gaian regulation? Well, if we think back to the Hadean Earth, about 4 billion years ago, so the first epoch of Earth's geological history, we often imagine scenes like this, where it's really hot and hellish. There's impactors coming. There might be very little liquid water on the surface. But the reality is that the Hadean Earth was not just hot, it could actually have been quite cold. You can imagine that an impactor hits, creates a planetary scale dust cover in the atmosphere, and that cools or heats up the planet depending on the dynamics of the impact. It's suggested that the Earth in the Hadean might have actually gone through oscillations in temperature and water availability. You had volatile rich impactors, you had liquid water on the surface, and then you got hit by another object and you lost a lot of that, right? The moon forming impact was certainly one of those events, but that took place way before we think life might have emerged, or at least caused extinction of any life that emerged. And this process would have continued to some extent even beyond that. We know that from the impact marks that we see on the moon. Today, the Earth's atmosphere and the planetary system is stabilized, but we want to contrast that with what was happening on the early Earth. So for illustration purposes, today, there is a positive feedback loop. If the temperature on the planet gets a little too hot, regardless of whether humans are the cause or not, it leads to the ice sheets, glaciers, and the polar ice caps melting. That changes the albedo of the planet. And so the ice is replaced by a darker sea and land, and that absorbs more heat and light. And that feedback cycle will continue, right? It will warm it more. And so this is a positive feedback loop. It's the ice albedo positive feedback loop. Today on Earth, it's balanced by a negative or regulating feedback loop. One example of the negative feedback loop is a silicate weathering cycle, where higher temperatures mean that you get increased hydrological cycle and you get increased weathering. So in a simple concept, high temperatures, more moisture in the air, more rainfall, more weathering, faster reactions that then absorb that CO2 and bury it back into the mantle. We'll see it in more detail, but that absorbs that CO2 and cools the planet. So both of these systems, if these were the only two operating, can balance each other out and keep the climate stable. And the silicate weathering cycle has been invoked, almost universally to explain how the Earth has managed to stay stable despite the increasing luminosity of the sun over the last 4 billion years, and changes in Earth's own climatic history as well. And here are some of the equations that go into this carbonate silicate cycle. As I said, essentially you have volcanoes or other sources producing the CO2 in the atmosphere at high temperatures that will start reacting, and in rocks and mountains in particular, and then can get sequestered. But because this is a temperature dependent cycle, it means you can have this negative feedback take place. But notice I mentioned that you needed mountains for this, and that's because that helps expose fresh surfaces where you can have this weathering take place. Now, to build mountains like we see on Earth today, like the Himalayas or the Alps, very close to where many of you are joining from, you need plate tectonics. Now, without plate tectonics, the silicate weathering feedback cycle was inoperative, or at least inefficient in the first billion years or so. When plate tectonics got started on Earth is still uncertain, but we think at least for the first billion years, the mechanics required and the properties of the slab, of the mantle and the crust were not conducive to plate tectonics as we would understand it to take place that would support this mountain building activity. In addition to that, the contribution of C4 weathering in that early part of Earth's history is uncertain. So we have a situation where this particular feedback cycle, which has been invoked to stabilize the Earth today, is not actually available to us in the first billion years of Earth's history. So we are left with this dilemma where we need to find some negative feedback to balance these positive feedback loops which were present in Earth's first billion years. Silicate weathering may not be as functional or operative. There's another one, which is the cloud albedo feedback. Essentially, if you have high temperatures, you can get more clouds forming, and then if the clouds are at the right altitude, you will be able to reflect more light back into space and not warm the planet as much. But it's again not well understood in the early Earth's atmosphere what those cloud dynamics were. So what happens in that situation? Does the Earth run away? Well, we know that in Earth's case that didn't happen, but perhaps that happened on Venus and Mars. Now, perhaps we can invoke biology to fill in some of these cycles. Could it be that biology enabled some silicate weathering or formation of hazes or clouds that were providing the negative feedback? This idea is known as the Gaia Hypothesis. It's attributed to Lynn Margulis and James Lovelock in particular, and was developed in the 1960s and the 70s, way before my time, but it still holds true today. And these are some of the seminal papers that describe this. And just looking at the titles for now, notice the biotic enhancement of weathering and the habitability of the Earth. Atmospheric homeostasis by and for the biosphere, the Gaia Hypothesis. We suggest that the Gaia Hypothesis, or the process of Gaian regulation, could be crucial for the first billion years of Earth's history. We know today that biology is part of this cycle. Here, for example, we've got the same positive feedback loops we've talked about before. And in here, we've got a situation where higher temperatures lead to increased vegetation cover. Now that could decrease dust supply so that you have reduced marine productivity, essentially because more vegetation means you don't have as much soil erosion, and reduced marine productivity means you don't absorb so much CO2. So that ends up becoming a positive feedback loop. Or you could have a situation where vegetation like lichen help the chemical weathering process and physically breaking up rocks and increase the rate of CO2 removal and burial by enhancing the silicate weathering cycle and cooling the planet. That's what the main Gaia hypothesis that Lynn Margulis and James Lovelock were talking about. But there could be many other ways that biology is involved. For example, it's been argued that organisms today can produce things like dimethyl sulfide that actually nucleate and activate the cloud condensation process so that it can control how much cloud cover there is. But I want to think more generally beyond today. Over the last 4 billion years, we know that life has co-evolved with the environment on Earth. It hasn't lived independently of the environment. Ever since the emergence of life on Earth, no matter what domain of life we think of today, they have all co-evolved, and they have done so in response to changes in the atmospheric properties, in the oceanic properties, the geochemical environment that they existed in. Here is just one example where it traces the evolution of certain metals over the last 4 billion years. And all these rather dramatic changes, noting there in the log scale, in both the composition of the atmosphere and the redox state of the oceans and the availability of certain metals, was all supported by evolution of new metabolisms, essentially. A lot of it can be explained by the emergence of oxygenic photosynthesis, but it's not the only one. There were lots of fluctuations all across this time domain, which are not shown in this figure, which could potentially be attributed to new metabolisms or different metabolisms coming in and going over life. What I mean by that is, if we think about all the different metabolisms that exist on Earth, in life as we know it today, here is a diagram that tries to make kind of a subway view of the different metabolites, different molecules that can be used for carbon fixation or for energy production. And a lot of these processes are linked to geology or to the geochemistry of those organisms. They don't happen independently. I think it's reasonable to say that metabolisms arose to take advantage of the geochemical gradients that existed abiotically, but also that life could have enhanced the pre-existing gradients to be able to extract more energy from the environment. Over time, life created, co-opted, and mediated other geochemical gradients. It worked across air-water interfaces, across hydrothermal gradients, and it led to the emergence of microbial communities that had to work together, that had to live together. So, taking that idea of geobiological cycles to the Gaia hypothesis, what we are suggesting is that these things may have actually played a role in stabilizing the climate of the Earth. It wasn't just silicate weathering that stabilized the planet, it was probably life as well. Is it just a coincidence that the molecules most used by life are also greenhouse gases involved in the climate feedback cycle? Water, we know, is a greenhouse gas. So is CO2 and methane, we all recognize that. But hydrogen, an energy source for a lot of organisms, and in fact a building block molecule for methanogens, and N2O are also greenhouse active gases, depending on the processes and the state of the atmosphere. This idea is gaining increasing recognition in the community. Many of these individuals you will often recognize as co-authors with people in the room here. And the idea that life is increasingly a part of Earth's history and could have been crucial to the stability of the planet was not something that was entertained, I would say, 10 years ago, but is being championed now to some extent, particularly by folks like Colin Goldblatt. And I'm going to read just a paragraph here because I think it puts it really well. The boundaries of the climate states are determined by atmospheric physics with abundances of these gases as a free parameter. We can move all these knobs to try and stabilize the planet. But on Earth, appeals to physical feedbacks to control CO2 or dinitrogen inventories fail. those parameters are controlled by geology, geochemistry, and life itself. As we view Gaia through the atmosphere, we see that habitability and inhabitants are inseparable. So biology is no longer just a result of a habitable environment, but rather an active agent of habitability. Indeed, over the next few billion years, things will change on Earth and things will die, in large part because of the increasing luminosity of the sun. Here's a figure you can look at in more detail. In about 1 billion years, essentially, there won't be enough liquid water to sustain the life forms that we are familiar with today. So we are okay with the concept that Earth's habitability has evolved over time. There was a time 4 billion years ago when there was the possibility of the emergence of life, but is no longer the case today. Today, there are habitable conditions on Earth, but in 1 billion years, there won't be habitable conditions on Earth. Why do we suggest the emergence of Gaia regulation is rare or slow? Well, it comes down to this idea of being quirky. Biology, unlike chemistry or physics-based processes, is allowed to be quirky and therefore rare or a time-consuming exercise. Just like English is a quirky language, it is a rare language in the universe, biology is one of those things as well. And it's because there are stochastic processes that lead to biological outcomes. We would suggest that a physics-only, biology-independent habitable zone is transient. What I mean by that is, if we think about the Earth today, where it's quite stable, there's a negative feedback loop that balances positive feedbacks, is stabilized by things like the carbonate silicate cycle, but it's also supported biology. There's the saddle where things are stable. But 4 billion years ago, without life, we suggest that if you just depend on the physics of the planet and its host star, that its tendency is to fall off this point over here. What this means is that extinction is a cosmic default for most life. Generally, things go extinct in the first billion years, and very rarely do they survive to the point that we have on Earth today. And that's because planets essentially fall off this point in most cases. Because to have complex biological systems, metabolic pathways that are on a planetary scale that can regulate the atmosphere is hard. It takes time. And if you don't do it in the first billion years, chances are your planet will run away. So I want to finish with this figure over here, where we are suggesting that the Gaian bottleneck is an idea that even if the emergence of life is a common occurrence, the evolution of biotic regulation of greenhouse gases, or albedo, needed to maintain habitable conditions in life is a rare and random adaptation. Earth could be unique in that respect. Perhaps if you think of that figure with Venus, Earth, and Mars, we all had the emergence of life, but maybe only on Earth did it evolve in a way so that life could interact with the atmosphere. It learned how to co-opt the geological cycles and the geological conditions for its own advantage. And this could be one more solution towards Fermi's paradox. This figure tries to explain that. I'm going to leave it in the interest of time today. We can come back to it. But this hypothesis does lead to some testable predictions. One prediction is that most habitable planets will only show fossilized signatures of past life. So if you were to point our telescopes to stars and try and search for life, what we'll probably see, according to this hypothesis, is isotopic signatures, perhaps in the atmosphere of planets, because planetary instability snuffs out incipient life. Most of the time, life starts up but goes extinct. And so you'll see dead planets. Another prediction is that if you were to look at biosignatures, and we did find them, they would tend to be from younger planets, less than 1.5 billion years, because life on those planets is still active. It hasn't had to go through the Gaian regulation requirements yet. And finally, another option might be just to go to Mars and look for life, signs of life there. And what this hypothesis suggests is that life on Mars will be communal, because we know that happened on early Earth as well, but not sufficiently integrated with planetary scale atmospheric regulation. That is to say, we shouldn't see isotopic signatures in the rock record or in the atmosphere of Mars that show that life on early Mars was able to regulate its atmosphere like life on Earth is doing today on Earth, on Mars as it is doing today on Earth. A universe filled with dead aliens might disappoint some, I admit that, but I think you'll all agree the universe is under no obligation to prevent disappointment. I'd like to leave it there, and thank you very much for your time. I'll start. I can see there's a lot of comments here, and I will pass it over to Tillman. Thank you.
Thank you very much, Aditya, for this nice and very thought-provoking talk. And yeah, there's already lots of comments in the chat. Just let me remind you that you have two ways of posing questions to Aditya. Either you write your question in the chat, and maybe not such a long question so that I can read it to him, or you raise your hand using the raise your hand feature, and then we will give you the floor. So we'll be switching back and forth, between the two. So let me start with the chat. I mean, there's a comment or a question by John Rummel. But the Burgess shale provides evidence of massive adaptation, even if you think the results are comic. You want to comment on this, Aditya?
I'm going to ask John if they're able to maybe come to the microphone and explain that comment a bit more, because I think it's open to so many interpretations.
Okay, then there is a longish question. I try to read it to you. Hi, Adi, nice talk, and so forth and so forth. Do you see any possibility of such galactic life or its main molecular building blocks could survive from the star formation and then be inherited into our protoplanetary disk, maybe the outer part, and then accreted together with rock-forming materials to form a rocky planet like our Earth? Of course, it's another question whether such accreted life would survive the first several million years of the Earth's formation evolution or not, nor it would exclude the popular scenario that life was emerged in the terrestrial environment only after a few million years of after planetary formation.
Yeah, thanks, Hayang, for that question. And I think you are alluding to panspermia, but in this case, interstellar panspermia, where you could have life emerge, maybe even be Gaian life. So that is, it has learned how to change its planet and keep it habitable for billions of years. Could that transfer across to a new planetary system? I remain skeptical. I think we don't know enough. There are some signs that life can actually survive on meteorites and asteroids, for a very long period of time, especially if it's of a microbial nature, right? So I think there's potential in that. But the time scales we're talking about when it comes to interstellar travel is orders of magnitude more. And so it's not clear to me whether even microbial communities which need very simple energy sources that you can imagine in a hydrated environment, or perhaps as a dormant spore on a particle or rock that has been ejected out, is a viable option. But I don't think we should completely dismiss that. The other part to this question is, okay, so if let's imagine you do get Gaian life that has evolved on one planetary system to another planetary system, will it be able to quickly enough adapt to the new environment? It won't be the same environment that it's evolved in before. And so we need to make sure that we appreciate that, it only has, let's say, 1 billion years before the new planet runs away as well. And so I think it remains an open question, but it's a great thought, and thanks for asking that.
Okay, let's switch over to the raised hands. So William Ball was the first to raise his hand, and Willie, could you allow William, give him the floor?
Hello.
Hi, William.
We can hear
yeah.
you. Just start your question.
Yeah, I just wanted to, a couple things. One is thank you for, it is a thought-provoking talk, as others have said in the comments. When you're talking about the Gaia hypothesis, then I start thinking about, well, human beings. If you talk about indigenous peoples, they've pretty much conformed with the Gaia hypothesis, but then Western civilization has overrun the planet, which is rather anti-Gaia. So how do you fit that into the Gaia hypothesis? Or maybe that's what you would call quirky life?
Mm-hmm. Certainly. And, I'm gonna, so that just for illustrative purposes, move to this figure that we didn't really talk about and just focus on the last panel. The way I would interpret it, and I really appreciate your comment about, indigenous communities and let's say the non-indigenous ones, or more like, I guess, the ancient ways of doing things versus the modern way of doing things.
Right.
I agree with your sentiment, particularly in Australia, we see this where we've got, more than 60,000 years of indigenous history and maintaining the land and taking care of it and those sort of things. There are lots of parallels with Gaian regulation, even at a planetary scale. The way I would like to answer your question is to say that, notice this green line, this is meant to be Earth, and Gaian regulation keeps it within this temperature range that's comfortable, right? Now, right. You can imagine that there are life forms on Earth that in some instances were anti-Gaian. They, for their own well-being, because they didn't care about others, or capitalist models or whatever you want to call it,
right.
Were pushing the Earth in another direction. What we would say is that is another opportunity for the bottleneck. It's not just that if life passes the first Gaian bottleneck, then it will remain habitable for billions of years. This is only the first and perhaps the major one. But I'd like to suggest that once you make it through that, the organisms that survive are the ones that know how to take care of it. And in the human analogy, even as Western civilizations or modern civilizations, we still recognize the value of the traditional ways of taking care of the land and the environment. And that's why we do the kind of things we are doing at slow pace, perhaps, but we're trying to manage that because we all came from the same ancestry. So it's plausible to me that maybe there aren't actually that many anti-Gaian organisms after the first bottleneck event, because they all have a common ancestor who was Gaian too. Does that help in a weird way?
Yeah, it does.
Question?
I think the ones who are most anti-Gaian, it's driven by a few rather wealthy and greedy individuals that are basically driving a lot of what's happening. So yeah.
Okay, let's move on to Tomasz. Tomasz, would you speak up? I hope I pronounced your name correctly. Thomas, go ahead. You have to unmute your mic.
I just wanted to thank you for a beautiful talk, and that was a mistake. Sorry, I lowering my hand. Sorry.
Okay, thank you very much. Now let's move back to the chat. Frank Paul asks, how important are repeat extinctions of life to get to the intelligent life we have today?
How important are repeat extinctions of life? Yeah, this actually relates to an earlier comment as well about what we mean by intelligence. I think extinction events can lead to a lot of diversity. I think that there's good evidence for that in the fossil record. I'm tempted to say that, there's not a tendency for intelligence to evolve. There's a really nice talk that I can point to by Charlie Lineweaver and a paper on why I'm making that statement on why intelligence is not something we think is a common feature of life in the universe, because we don't see a tendency for that on Earth. But despite that, I would say that extinctions or massive selection events, is perhaps a more general way of putting it in, are the way to have diverse metabolisms arise, diverse and not just geochemical metabolisms, but social metabolisms. And I think intelligence would be part of that spectrum. Hopefully that answers very briefly in a vague way your comment. Thanks.
Okay, Keith Horn asks, most stars are much cooler than and live much longer than the sun. How would this affect your scenario, considering early extinction to be more likely or less likely?
Yeah, I think, Keith, that's an excellent point. So today I've focused on sun-like stars and alluded to the billion-year or so time scale over here. There's this yellow region here. But with smaller and cooler stars, this time period may change. I'm not completely sure in which direction it will change, because a lot depends on what that means for habitability. So I would have to go and kind of read up on that a little bit more. But even if it's a M star, for example, which I understand is cooler, if I'm right, the time scales are not going to be orders of magnitude different. We are still talking about, instead of 1 billion year time scale, you've got 1.5 billion or so. So it's not, I don't think it's going to suddenly be 10 billion years or something like that. Of course, the other issue is how the A and Z corresponds to those stars. I think that's not as well understood as we understand sun-like stars, because we live around one. We've modeled them, I think, more than other stars. Thanks.
Okay, thank you. So John Rummel has a comment, but let's maybe switch to the next question by Mark Sargent. And that, I think, is an interesting and valid one. In your figure, you generally show planetary environments evolving away from the habitable conditions. Is this by far the most probable scenario, or is there some likelihood that the environment would leave and then return? Or stay, I would add, and then return to habitable conditions, extinctions followed by re-emergence of life, or emergence potentially made easier if the planet has already at some point hosted life. So I think the question basically is, is your conjecture that planets move away from habitable conditions, but is that necessarily so?
Yeah. Look, I think it's a really good question. If we think about those tube-like figures, they often move away from habitable. That is more a function of trying to display it in a 2D version for publication and for simplicity. But you're absolutely right. There could be times when it becomes more habitable. Now, Mars is one example of that. in the next 500 million years to 1 billion years, there will be enough solar luminosity increases that Mars will start melting the polar ice caps and have liquid water on the surface. So in one sense, it will be more habitable. The problem though is Mars will probably not have hydrothermal systems or plate tectonics at that point. And so it will be lacking in the conditions required for the emergence of life, assuming that those are some of the conditions required for the emergence of life. What that means is that, even if something becomes more habitable in the future, if it missed the boat to get inhabited by life, either because of emergence natively on the planet or coming through panspermia from exchange during the early part of the planetary system, it doesn't make a difference. It's too late. So you remain in that scenario an habitable but uninhabited planet, right?
Okay, thank you. I think this exhausts the questions that we have in the chat. And with that, I join, the many thank yous that are here written in the chat. Thank you very much, Aditya, for the inspiring talk and for getting up so early in the morning, to give us this presentation. Just let me remind you that next week, unfortunately, we had planned a talk on biosignatures and signatures of habitability, but unfortunately, the speaker had to withdraw, and so next week we will not have a Game Changers presentation. Then in 2 weeks' time, we will have a talk on space weather, space climate, and habitability by Thierry Dudok, excuse me. So thank you very much, and I hope to see you in 2 weeks' time. And Aditya, have a very nice day down under. Thank you.
Thank you, everyone. Appreciate it. Thanks for the fantastic comments. And if I didn't read them earlier today, I will get a copy and browse them through.
Yeah.
Thank you very much for having me.
Yeah, Willie will send you the comments in a file. And again, this is recorded, so if you want to revisit the talk, you're welcome to do so by going to our webpage. Okay, bye-bye. Have a good day. Thank you very much.